Hello to everyone. In the following presentation, we would like to introduce the method we used and the results obtained for the three-dimensional reconstruction of the plaster cast of the Toro Farnese. In the overview, you can see that we want to address some important aspects here, and due to the short time available, we will start right now. Let's start with the central object of the scientific study. Here we see the Toro Farnese, a massive Roman copy of a Hellenistic sculpture. It was discovered during excavations in 1546 and dated to 222 to 235 Anno Domini. It was carved from a single block of marble and is considered the largest single sculpture from antiquity to date. The original is in the National Archaeological Museum in Naples. A 3D model can be found at Sketchfab with 570,000 vertices and 1.1 million triangles. The model provides a very good overall impression of the Toro Farnese, but the middle image shows that the resolution is not suitable for more precise analyses. There is an old complete plaster cast in the cast collection of the Free University of Berlin. Another, slightly incomplete model can be found in the Antiken Museum at the University of Leipzig. The sketch on the right shows the individual pieces and the missing elements in red. A number of scientific questions can be derived from this situation. An important milestone, however, is the digital reconstruction of the individual parts in Leipzig, as well as the complete sculpture in Berlin. When entering the topic of digital reconstruction, we should first clarify the term 3D reconstruction. There are two fundamentally different approaches that can be described by the term 3D reconstruction in the context of archaeology. In the first case, digital 3D models are reconstructed by a human using digital tools based on excavation plans, drawings, traditional descriptions or illustrations, and analog finds. This is what we should call reconstructive 3D modeling. In the second case, camera or measurement systems and computer algorithms are used, which can mathematically derive the object structure via the read-in data. In both cases, the result is a digital 3D model. In the further discussion, we will exclusively consider the second case, in which image captures are algorithmically merged into digital 3D models, and use the term 3D reconstruction as a synonym for it. The methods shown here can be excellently applied in the archaeological context. In terms of mobility and cost efficiency, image-based methods such as photogrammetry are the best option in most cases. We can understand videogrammetry as an extension of photogrammetry, where videos are extracted by intelligent image selection. The question arises as to whether videogrammetry is also suitable for such a challenging task as the 3D reconstruction of the Toro Farnese. Is it a useful alternative to 3D laser scanning? This question is probably in good hands in our working group, as we have been working with videogrammetric methods since 2013 and have introduced them into archaeological documentation work. We have accompanied many archaeological campaigns above water with multicopters. Since 2015, we have also accompanied campaigns underwater with several mini-submarines. In recent years, we have started to combine the advantages of both approaches. To mention just one important point here, videos do not have geo-information. The geo-tags contained in photo recordings now also allow automatically geo-referenced 3D models that were recorded via videos. If you have not yet heard of videogrammetry, this short formula gives you the main idea of videogrammetry. Take a video of an object or site of interest, select the right images, we call them keyframes, and use the power of photogrammetry to detect 3D information out of these keyframes. Breaking down a video into frames doesn't sound very challenging at first, but we need to understand two important things here. The smaller the distance between the selected images, i.e. the greater the overlap, the more 3D points are possible later in the 3D model. However, if we were to take all the images, this would result in fewer 3D points than if we were to take a smaller selection of images. The reason can be found here. The greater the image distance, the more precisely the points can be localized, and only well-localized points will later become 3D points in the model. if we choose too large a distance, incorrect assumptions or disconnected models can result. Over the last more than 10 years, we have developed many algorithms to solve this task, and with Keyframer, we have programmed a stable solution that delivers very impressive image sets. If image-based methods already have so many applications, what are the challenges of a 3D reconstruction of the Toro Farnese? For many people, photogrammetry is like a black box into which photos are entered, and, in best case, a 3D model appears. However, there is a lot to consider when taking photos and videos. In the example on the left, we can see how sensitively the extracted features, i.e. the potential 3D points that later end up in the model, react to lighting. In the right-hand image, we can see that lighting is not everything, as the focus also plays a decisive role in extracting the features. We therefore need to ensure good lighting and sharp images. We are dealing with a plaster cast, and these usually have a smooth, regular structure with very few visual features on the surface. Usually when we record videos, we try use action cameras like the GoPro or our own smartphones. We often use a stable video stream of 1080p at 30 frames per second. The following example, which was recorded as a video with a Samsung Galaxy S20, shows that this can make sense. We can see in blue that 20,000 features were identified, from which 4,600 were later actually transferred to the 3D model as 3D points. The two biggest challenges, however, are the size and complexity of the structure with its filigree elements. In addition, the model in Berlin is positioned next to the wall and cannot be moved. Furthermore, the open windows above and next to the sculpture have a strong influence on the lighting and therefore the shadows. But before we start the large-scale project, a few practical tests should be carried out on the parts in the Leipzig collection. We went on an excursion to Leipzig with students who had just attended the lecture 3D Documentation in Archaeology in our new master's program. There we discussed which recording strategies are suitable and how to approach such a project. We concentrated on a few larger parts. Everyone had the opportunity to use their own smartphone for recordings. You can see from the photos that we focused in this example on the part labeled TF10. At the top left, we see a video recording that is about 5 minutes long. Below, we see the individual photos selected by Keyframer as white dots and the resulting model in reality capture. With 3.7 million vertices and 7.3 million triangles, we were able to create a very promising textured 3D model. I would like to mention the great collaboration with colleagues from Berlin and Leipzig, which we have on both a scientific and student level. Thank you very much for allowing us to try out our theoretical concepts in practice. So, the results made us optimistic, but the Toro Farnese is the most complex structure we wanted to record by hand in the project to date. Once again, this is what the conditions looked like when the Toro Farnese was recorded in April 2024. The aim was to take enough pictures within 2 hours with a smartphone using a ladder and a tripod to successfully reconstruct the Toro Farnese in 3D. In order not to lose the overview of this complex recording, the first step was to name various views based on the digital model from Naples and prepare them for notes. In the second step, the planned recording sequences were carried out, and the recording corpus was directly sketched and noted. I can speak from experience that it is absolutely essential to consider the structure and special features in advance and to prepare strategies for the recordings. A high level of concentration and a steady hand are necessary when recording in a chord. In the third step, the videos are to be broken down into a number of individual images by the Keyframer. By the way, if you are interested, the same version was used here that was released with the book published in 2024. The set of individual images is then finally processed using the almost standard pipeline of reality capture. Okay, let's take a look at the results of point 2, where the capture strategy used is relatively easy to recognize. Here the white dots are again the selected individual photos from Keyframer that led to the pose estimation in reality capture. On the left, we see a kind of helix flight with different distances and heights, which we use very successfully with multicopters. In the image on the right, we continue to recognize typical grid-based flight patterns with numerous intersections. Additionally, in the left and central images, it is very clear that inner shots must always be connected with those taken further out. This is by far the biggest challenge and requires some practice. In less than 2 hours, 8 videos with a total time of 42 minutes were recorded. In just under 2 hours, Keyframer extracted all the individual frames from the videos, generating a data set of almost 46 gigabytes in the meantime. In a further 2 hours, just over 12,000 keyframes were then selected. Reality capture in the current version 1.3 was used for the reconstruction. The standard pipeline was slightly adapted so that the image overlap in the alignment also allows medium, and the mesh model is only produced in normal detail on the computer currently used. It has been shown in the past that it makes sense to bring the image packages of the videos together one after the other with the so-called iterative alignment. This has the advantage that an error can be identified more quickly and the calculation does not have to run through all the matches first. The final model we see here has more than 20 million vertices and more than 40 million faces. The model is already of very high quality and has a high level of detail. However, it is still easy to identify faulty elements. As we can see here, hidden areas that are difficult to access sometimes indicate a need for further video recordings. In summary, it can be said that videogrammetry is a candidate for 3D reconstruction of complex structures with difficult surfaces, such as plaster. It is very easy to use with a smartphone, by example, but requires some experience and planning. The following can be said about future work. Further video sequences will be added to complete the Berlin model. It will be published and made freely available in the future and will serve as the basis for the missing parts in Leipzig. If you are interested in the background of photogrammetry and videogrammetry, if you are looking for data packages and practical examples, if you are looking for solutions in case things don't go as planned with the reconstructions, then my book might be a good starting point for you. In addition to an introduction to the use of cameras and learning how to use multicopters, there are also aspects of underwater archaeology. You will also learn how to perform archaeological documentation with mini-submarines. Last but not least, we see that in addition to numerous data packages from the last 10 years of documentation, even a part of the Toro Farnese in Leipzig is being discussed. Thank you for your attention.